So, we will continue with this planning of sampling, that was the first part. The next, we have to look at these decisions to be made based on the information we have got. So, whether we will go for manual or automatic sampling, it depends on what are the facilities, what are the requirements, that is dictated by the previous one. Okay. Sampling frequency, as I said, that how frequently you want this data, sample sizes, in each increment how much of sample I have to collect, because based on that you have to devise your container and your sampling program and all this. Sampling locations, that is very important. What do I sample in a running plant? What are the locations? Okay. Then individual versus composite samples, what does it mean? That means suppose if I am collecting hourly data, then at the end of the day I will be having 24 samples. Should I mix all of them and then redo the sampling and then take 1 gram of sample and do the analysis, or do I need analysis for each sample collected each hour? That is also basically the decision we have to make. Sampling strategy, random selection, stratified random selection, systematic stratified selection, that is the what is the procedure, what is the stochastic route you will follow. Okay. Training, that is very important. The people who are basically the part of the sampling campaign, are they trained? Are they fully aware of the procedures and the likely consequences in the sampling? Okay. That is very important. So, plant sampling, very simple clue is that always try to sample from a moving stream. When the material is flowing, it is from a moving stream. The best way of sampling a moving stream of ore, concentrate or slurry is using a correctly designed sample cutter. How do I design it correctly? That is the dimensions we have discussed. At the discharge point of a conveyor belt, chute or slurry pipe, that means where it is discharging, at that point you should have a cross cutter of the stream. Then you are not introducing any bias, otherwise that example I have shown, you will have this problem. Okay? Delimitation error. The stream can be intersected at random or regular times, or tonnages and representative samples called increments can be collected by taking a complete cross section of the stream. That is very important. You have to cut the complete cross section, not the part, with a cutter, thereby enabling the increment delimitation and extraction errors to be eliminated. Okay. So, moving stream, and you must cut the entire cross section. On the other hand, sampling devices that take only part of the stream, I will show you what normally in industry the common mistakes are. That is, you take a small sample from the small portion of that moving stream, and that will induce a bias. Okay. I will show you. Okay. Like is a schematic of a falling stream sample cutter, that is a falling and it has to move, that I have shown you that what should be the design of this. I have given you some examples, some dimensions, but it should match based on those basically formulas, you have to design that. Okay. Incorrect sampling, normally we do it. Suppose this is called a shark fins. Say I have got a flow, okay, like suppose you want to do the wastewater analysis. Okay. You are working on environment and you have got a wastewater stream and you want to analyze that what is the level of pollutants there. So, it is a wide stream. So, what do? You put a small fins like this and you collect a part of the slurry and you say that is my sample. But what will happen? Now, if my pollutants are getting transported across this, So, at different depth you are having different pollutants, because as I said that at different layers you are having different velocities, and at different across the width at different locations I may be having different things. So, if I am taking only a small portion, if I am not cutting the entire stream, so I am introducing a bias, I may miss some of the particles which are bypassing that, and that is a very so you cannot cut it short, you have to have some methods of cutting the entire stream across. Very common in our mineral processing plants or where we have got slurry flow problems and all this, slurry is coming through the pipeline and you make a small hole at the side and you take a bleed of that sample, very common. Many industry people, they are smiling, but that is incorrect. Why I am saying? Again, that particle which are basically what you are sampling, that is a slurry which is close to the wall, and that is also in one direction. So, from the middle what particle are going, that could be different what you are collecting from the side. So, you may not be having the actual picture. So, that is a wrong sampling campaign, you should not, you cannot do it like this. Okay. So, what I have to do, where the slurry is basically delivered through the pipelines, at that point can think of, based on your planning of sampling requirement of that, you can have a cross cutter. You have to cut the entire cross section of that, otherwise your sampling will introduce a bias. Okay. That is a correct sampling procedure. This is what I said, that if your cutter is not properly designed, or maybe the velocity moving speed is very high, you may miss some of the particles that may go out from the system. And suppose I want to collect your 1 kg of material per increment. So, that 1 kg is not sufficient to know what should be the volume of that, and then I must know that there will be some air or water also with that. So, if my design of container is only say able to accommodate 1 kg of sample, but if I am not considering volume, so what will happen? There will be spillages. So, you will be missing some of the particles, so you will be missing the slurry, you cannot do the flow rate analysis and all this. Okay. So, you have to know the basically the cutter volume and all this. So, most automatic samplers operate by moving a collecting device through the material as it falls from a conveyor or pipe. It is important that the face of the collecting device or cutter is presented at right angles to the stream. That is the first one. Number 2, the cutter covers the whole stream, not the part of the stream. The cutter moves at constant speed, there cannot be a variation in the speed. So, that means there should not be any vibration, motion should be smooth. The cutter is large enough to pass the sample, that is 3 times or greater than that of the largest particle. Sampling of smelter products, residues and wastes for metallurgists, you know. Sampling of molten smelter products is particularly very difficult. How do I cut the entire stream? Suppose your molten metal is being poured into a ladle, how do I cut the entire stream? It is very difficult, and then I will be losing some of my metal also, and it is risky also. So, but the good thing about the molten metal is that the material being sampled is molten, it tends to be more homogeneous than particulate material. That means it behaves like a fluid. So, I can take a small unit and I can dip it and can get that. Not much of bias is there, because if they are all in molten stage, but if I have suspended particulates in that, then again I will have bias induced into that. If I have your smelter residues, like say suppose blast furnace slag, I want to know that how much of lead is there, or how much of chromium is there, how much of iron is there, and there is a slag heaps is there. Now, they are all basically behaves like a rock. So, how do I take it? So, normally the practice is the industry people, what do they do? They just try to drill holes or some side walls and then they take a representative sample, but no, you have to grind the entire sample, otherwise you cannot. But you may laugh at me that how do I do it? So, the best way of doing that, when the blast furnace slag heap is being formed or being basically dismantled, That time you should take the representative samples by putting them into a moving stream based on the GUI's formula, how much of sample I should take, then you further grind it and then come to the laboratory and you use some other techniques for laboratory sampling techniques to get the samples. You cannot do that. Okay. Similarly, for stockpiles, you said that stockpiles normally what we do, we take samples from sites, we take a scoop and we take samples, but how do you know what is inside? I cannot guarantee that what is inside. So, how do I sample a stockpile? You know what is stockpile? Stockpile means where I am throwing my rejects, or maybe I am just dumping my material for further processing or maybe for storing purposes, that is a stockpile. Okay. So, it will be unreliable. So, what I have to do? When the stockpile is being formed, that is when I am delivering the material to the stockpile, that time it is moving, that time I should have a cutter. Or maybe when I am basically, why I need to know what is there in the stockpile, that means I want to do something with that. So, let it move, that means let us first say dismantle that, let me first say reduce the say actually put it into a material handling system and then let me do that. Or otherwise what I have to do, if it is not possible, then if it is fine granular material, if you know that they are in finer stages, and then I can use some auger, and auger you have to cut it across at different heights and all this, and you take samples from different locations, but that will still have errors. Okay. So, if it is unavoidable, you have to do that. That is why I have written the only reliable way of sampling materials such as ore, concentrate, matte and smelter residues in a stockpile is to take samples from a moving stream as the stockpile is being built up or broken down. That is the ideal case. Sampling from sieves, trucks and wagons. Wagon sampling, that is a big issue in coal. The issue is that you are delivering coal, that is a Coal India, say suppose, and main client is NTPC. So, there is a mine site and it has to be transported to the your user NTPC site, and then what they are doing, when the Coal India is sending, that they are saying that this is the grade of my coal, and when NTPC is getting that, they again do the sampling and they do the analysis, what is the grade of my coal. So, Coal India asks, Coal India says that we charge money based on the what is the grade I have delivered, but they say that no, we will pay the money based on what we have received. So, what happens? The NTPC people, they start doing the sampling from the wagon. If you go there, you will find that there is a rake consisting of 58 or 59 wagons, I do not remember the number. They choose randomly 5 or 6 wagons, and some people they climb up the wagons and then from there they collect some particles, but how they are collecting? How do you know? On top of that, if there are only stones, you are only collecting stones. So, that is a heterogeneous mixture. So, from the wagon it is not possible to do a take a correct sample. So, what I suggest that ultimately you are using a wagon tippler, it is going to a bunker, from that bunker you are having chute and then you are basically transporting it through a conveyor belt. So, why do not you do it in a conveyor belt, it is in a moving stream, why do not you sample it from the moving stream, then your entire problem is gone, then your sampling is much accurate. From wagon it is very difficult to do sampling, you cannot do, basically it is not ideal, but it is being practiced. Okay. So, I gave this example, say suppose I am carrying sand in a truck and I am the police officer, I got the information that maybe some arms are being smuggled through those sand trucks, maybe some 10 revolvers are there inside. But as a police officer, how do I make sure? I just climb up the truck, just remove some of the sand on top. So, nobody will put it there, they will put it somewhere in the middle or maybe at the bottom. So, how do I reach the bottom? How do I make sure that I have checked? So, the best way of sampling that, ensure that no arms or nothing is being transported which is illegal. So, at the time of basically pouring my sand into the truck, my people should be there. or maybe, and then during transportation it should be all sealed, and then when you are again delivering at the discharge point, there my people should be there. Then you must ensure, then only you can ensure that whether there is something other than your sand, okay? Otherwise it is not possible. So that means it has to be in a moving stream, because that is in a static bed, you cannot do it, or you should not do it. But many times it is impossible to do that. So what we can suggest, that is, because of the smaller size, it is possible, suppose if I have very small size powder materials being transported through trucks on all this, it is possible to sample fine concentrates less than 1 millimeter particle size in situ in trucks and railway wagons using a spear sampler. Spear sampler means it can go to the depth, and then you can take samples from different locations automatically, you can collect the samples. Why I am specifying less than 1 millimeter, and then this is possible for damp fine concentrates, but not for dry concentrates or lumpy ores. Why? Why dampy? Why not with fine? Because the dampy one will be little bit sticky, and during transportation there is hardly any chance for segregation. Otherwise, if I am only say taking sample from here, and I may be having different samples from there because of in situ gravity concentration, because if I have density differences, there may be some kind of jigging action because during the transportation. So I may not be having the accurate sample. So the best way is that when the truck is getting filled up or getting discharged, that time I should do that. Thumb rule, I would say that for coarse particles, for sampling, forget about G-wise formula and all this. If you are not comfortable with that, make sure that the coarsest particle in that population, you have selected at least 3000 numbers of particles. Coarsest particle, that is, what is the coarsest particle you have, and then you make sure that I have selected at least 3000 number of particles. Automatically other sample sizes will be more, and then you know that how many samples I have to collect. Okay? That is a thumb rule, some industrial practice I can say. Okay? Then sampling from vessels, a ladle is not recommended for metallurgical accounting due to the likely segregation of the material in the vessel. I do not know, maybe some particles have settled. So I do not know, I may be getting only the liquid. So sampling from moving streams as the vessel is being filled or emptied is recommended. Moisture sampling. Suppose I want to know what is the average moisture content of this, and you see that this is in open air. So when, that is when I have done this sampling. So there may be some kind of your losses of moisture because of evaporation. If it is humid atmosphere, I may be having more moisture than what it was. So while I am doing it, how do I preserve them? That is very, very important. Okay. Otherwise my moisture analysis would go wrong. So like that, that is, if I have collected it, I have to make sure that it is sealed before you bring it to the, at the point of collection, it must be sealed. You must ensure that it is not getting evaporated by moisture or getting contaminated with external moisture, and then you do the moisture analysis as fast as possible, as quickly as possible, otherwise you may get a wrong information. Okay. Now laboratory sampling. Now you have brought, that is what I have discussed about the plant sampling, but ultimately you do analysis at lab. Okay. Even in the plant you have got laboratories. Okay. So now how do I do that? Now suppose I have brought in my laboratory 100 kg of sample. Now I want again 1 gram of sample for analysis. From 100 kg to 1 gram, how do I do it? This is one method, that is called grab sampling. That means I will spread it and as flatter as possible, that means as thin layer as possible. Then I will take samples randomly from different locations with spatulas or something like that, or scoops. Okay. That is called grab sampling. Then this is most frequently used, that is called coning and quartering. So what do we do? How many of you have done coning and quartering? Okay. So why do I need to make a cone? Why do I need a cone? Why I try to make first a cone and then press it and then make it flatter? Why don't you start with a flatter one? Because by making the cone, I am giving the particles to segregate based on its own properties. And then when I am flattening it, I am distributing it equally. Otherwise, there may be a burst. If I just pour it and just flatten it, because the cone actually basically forms based on the angle of repose. And angle of repose is based on your size distribution, your density distribution, your other properties. Okay. So, I want to have a segregation of that, so that they are distributed properly. And then I will take a plate and I will flatten it. Then what I will do? I will make 4 sections of this, and the opposite sections will mix up, and these 2 will discard. Any 2, I may take these 2 and I can discard this. Why opposite one? Because I am giving equal opportunity, because these are already segregated. So, I am collecting all things. Okay. Then I repeat it again and again, then this one again I will make the cone. Do not cut it short, that I will not make the cone, then again you will have more errors. Many people do that. Every time you have to make the cones and then flatten it and then do it, that is the reason. Okay. So, that is called the coning and quartering, unless and until you get that your desired amount of sample. And a sample splitter, that is called a Riffle sampler. You have got riffles, and oppositely they are basically oriented 50% to this side, 50% to that side, and then you take your material in a your say container like this, and then you just bring the material like this and then you pour it, so that it is getting 50-50 distributed, and then 50% you discard, remaining 50% again you repeat that unless and until you get your desired quantity. Okay. This one is the rotary riffle. I can show you all this sampling equipment in my laboratory. I have this. This rotary riffle is basically, I have got containers of equal volume. It could be 8, it could be 12, it could be 16, depends on that. And then all these individual containers, I can dismantle them. But when they are basically put together, they make a continuum of this. Okay. And this is put into a rotating turntable which moves at a constant speed. Okay. And it is attached with a feed hopper and with a vibrating feeder, and your material is fed here, and then with a vibrating feeder that is also having some kind of your say flow rate monitoring system, so that the material is flowing through that, and then it is rotated at a constant speed. So, the material, that is basically I am cutting the moving stream at a right angle, and then I am distributing it into, depending upon how many containers are there, by 1/8 or 1/16 or 1/12. Then what I will do, depending upon the accuracy I need, I may take only one of this and I can throw others, you know. So, I am dividing it by entire population by 1/8 in the first go, next go again that 1/8 by 1/8, 1/64, then keep on doing it unless and until you get that. Okay. That is the rotary riffle type of system. So, if I do the error analysis of these methods, I have not done it, it is already done by others, and you see that if I have a random variation for a theoretically perfect sampler, an ideal sampler for a particulate matter, what should be the error? That is, the standard deviation of samples should have 0.076, ideal theoretically. Look at coning and quartering, it is 6.8%. Even if you do it perfectly, you cannot avoid this, but normally you get more than 10% error, because there are, we manipulate with this coning and you know all this, how do I mix it up and all this. Even if you do it rightly, you cannot get an accuracy level below this, that is already established. Okay. Then graph sampling 5.14, tube type of sample splitter 1.01, rotary riffle, that is why I always prefer for laboratory sampling the rotary riffle sampling. It gives me 0.125% of standard deviation. That is the best sampling device for laboratory practices, but it has cost me around more than 6 lakhs. I bought it from US even for that, because that turntable, that must be, there should not be any your vibration or maybe some kind of your dynamic stability problem. So, what happens when the particles are poured, there may be a dynamic stability problem. So, I may have different type of rotational speed, then I will have a wrong information. Okay. So, that has to be done perfectly. So, if I summarize the entire sampling lecture, I will say the basic rule for correct sampling, and sample processing is that all parts of the ore, concentrate, slurry or smelter products or waste being sampled must have an equal probability of being collected and becoming part of the final sample for analysis. If this is not the case, bias is easily introduced that cannot be eliminated by simply averaging replicate measurements. If the bias is already there, now it does not matter how accurately you are doing the analysis, how sophisticated your equipment is, doesn't matter, the bias is already there. Care must also be taken to ensure that sample masses are adequate based on the GUS formula, that you have your initial sample is up to that level. Okay. At each stage of sampling, that is even at each stage, that what is the tonnage of material, suppose from your say conveyor belt, I am decided that I will collect hourly basis sample. So, I must know that in an hour through that conveyor belt what is the tonnages of material I am basically conveying. So, based on that again go back to the GUS formula. So, I must know that in one increment I must collect that much of sample. It is not that it is at my wish, I will take 1 kilogram or at my convenience. So, it must be through that. Okay. It is difficult, but you have to do it. Okay. Determination of the moisture content and weight mass of the material being sampled are of equal importance to chemical analysis in metallurgical accounting. Why weighing is very important? Because it is all relative to percentage. What I am saying that I have taken 1 gram of sample, is it really 1 gram? Now, I am saying that it has got 5% of element X, 5% means is 5% of 1 gram, but there is an error in my balance. What will happen? If that is 1.1 gram, so I am getting a different information. If it is 0.9 gram, I am having different information. So, I must check regularly that what is the calibration level of that balance. Otherwise, that 1 gram will force me to spend, let us say actually few thousand crores maybe, because my entire information could be wrong. So, better you buy a better balance, do not try to save money in buying a balance by few thousand rupees to save few thousand crores, okay, which normally our industry people they do not understand. Okay. People will ask that why you need to buy a balance of 1.5 lakhs when at 15,000 rupees you can buy a balance, and then you show me my presentation that this is the reason. Okay. So, to minimize changes in moisture content, samples need to be taken quickly, placed in sealed bags or containers that are impervious to moisture and the moisture content determined without delay. To determine weight mass, it is important to select a method with the appropriate precision and ensure that the weigh scale is well maintained and regularly calibrated. Many times you will find that in your weighing balance there is already some leftover, the particles are already there. So, that is already having some weight. So, have you tiered it? So, make sure that. So, these are the guidelines of ISO, International Standard Organization. The guideline for coal and coke samples, that is minimum mass of sample for general analysis and determination of total moisture content. You see that is a function of size, a particle top size. So, nominal top size of coal, if it is 300 millimeter, the general analysis samples and common samples they should be collected 15,000 kg, 15 tons of material you have to collect. But come down, if it is 1 millimeter you need only 0.1 kg of sample, 100 grams. So, what I have to do? If I am going to the mine site, now it is your decision that whether you will collect 15,000 kg of sample of this size and bring it to IIT Kharagpur or your institute and then you crush it and grind it and do the analysis, or you will try to convince your person for whom you are doing the analysis, that is whether I should crush it and grind it at the mine site and I should bring 1 gram of say 100 grams of sample. But make sure that when I am basically breaking the particles, the surface are basically becoming very active. So, the reactivity of the surfaces will be more. So, that there will be a chance of chemical composition changes. So, I must send it properly. Specifically for coal, it gets oxidized very fast. So, if I am bringing to some place and I plan to do the analysis after 7 days or 8 days, you make sure that it is free from oxygen. So, what I can do? I have to put it into a container and you have to put some nitrogen or some inert gases to make sure that it is not getting oxidized. If that surface characteristic is very important for you to decide that which chemical I will be using for your flotation purposes. If it is for ash analysis, it may not be that important, but again I am saying what is the purpose of sampling, I must know. So, I have to take the precaution. Okay. So, and samples for determination of total moisture content for 300 millimeter, it is 3000 kg, and then you cannot do at these sizes. So, these are the sizes and weights it is given. For size analysis, if I want to do size analysis, if my top size is 300 millimeter, my minimum sample weight should be 54,000 kg, 54 tons. Okay. And you see that if you crush them, but how do I know then the size analysis if I have already crushed it? That is the problem. So, what I can do? I can get the information of the coarser sizes at the plant site. The remaining portion I will say that okay, I need my particle size analyzer to be used. Then I know that this is the top size for my particle size analysis, then I can reduce the amount of sample. But then the question will come, how do I integrate this together? That is the problem. That is why you need to have a correction factor for that. Okay. So, thanks for this.